Okay, so today what I'd like to try to do is sketch for you what I hope will be, well, a bunch of pretty explicit models with a lot of free coefficients in them, all of which have a lot of nice properties that we'd like to have for a quantum theory of gravity in four-dimensional Minkowski space with a certain particle content that I'll tell you about in a minute, and all of the models have a lot of properties that are compatible with those ideas. Namely, there's a scattering theory you can define. The scattering theory conserves energy. The scattering theory, as you'll see, is translation invariant, but making that happen is really a part of the construction of what the theory is. And every one of these models gives something that looks like local interactions between particles in small causal diamonds in space-time, but it also gives a process that looks like black hole production. And you can get all of the qualitative features of black hole production, the fact that the black hole has finite entropy and emits particles with a thermal spectrum with a temperature proportional to its Schwarzschild radius, that'll follow from all of these models. What we have not yet done, one of the consistency conditions for any quantum theory of gravity of our type, where by our type I mean that you do quantum mechanics along each time-like trajectory in space-time separately and impose all sorts of consistency conditions between those different systems for overlapping information. An important part of those words is that I cannot think of space-time as a fluctuating quantum variable. This is something that I think one can learn from Ted Jacobson's famous 1995 paper, where one thinks of the metric of space-time in general as describing hydrodynamic properties of whatever quantum system there is that obeys the area law. And one of the features there is that there's a consistency condition that it says if I describe space-time Minkowski space in terms of two trajectories that have a relative velocity, I should have a completely consistent description of the physics whenever those trajectories have overlapping causal diamonds. We have not imposed those conditions. That's a lack on our part, and we believe that it will put really stringent constraints on both what particle content you assume and also on the actual structure of the coefficients in the Hamiltonian. So in order to get on with this, let me just review these equations. If those of you who heard Andy's talk yesterday know that an interesting algebra of symmetry generators to think about in any asymptotically flat spacetime are the Bondi-Metzner-Sachs generators. And those are generators that if I think of them as functions on the sphere at infinity, are localized at delta function points on the sphere, and they have some positive or negative, if they're incoming momenta, energy flow into or out of the sphere. That defines actually two different copies of the BMS algebra, and those two copies are related to each other by the S matrix. And that was where Andy got all of his word identities from. Now, the other thing you can do, the BMS generators are all commuting, and they're all abelian. So you can use them to replace the sphere at null infinity by the null cone p squared equals 0. So the null cone p squared equals 0 records not only what angle you're at on the sphere, but also how much energy is going out at that angle. So what I've done is I've diagonalized the BMS generators.
You mean the super translations?
The super translations, yeah. Yeah, not the Lorentz group, of course. Right, here. Now, there is a generalization of that algebra, which was first invented by Iwata, Gibbons, and Shaw in a much neglected but also very difficult paper. This is my translation of the algebra that they wrote down. Actually, they write down two different algebras. I don't understand the other one. This one I understand. So these are generators that transform as spinors under the Lorentz group. The Lorentz group acts on this space. These transform as spinors. They satisfy these anti-commutation relations. Notice P and Q are both null vectors. This delta function of P dot Q says they're collinear. And if they're collinear, then one of them is larger than the other. There's an ordering, right? One has more energy than the other in the direction that they're moving. And this is the minimum of the two. That's the vector I put over there. So the P equals 0 guys anti-commute with everybody. Okay? Now, these indices I and J I've stuck up there in order to be talking about a specific spectrum that I know had better be realized in a concrete theory. Namely, if I take 11-dimensional supergravity, compactify it on a rectangular torus of Planck size in every dimension, a 7 torus, I get a 4-dimensional theory which has n equals h Susie, and that's the Susie algebra.
What about the central extension?
Sorry?
Like typically this, n bigger than 1, Susie algebras have central extensions.
Yes, so the central extensions indeed exist. They refer to particles that have BPS charges, and that's a much more difficult subject. You have to talk about massive particles, and there are a lot of things about it I don't understand, so I'm not going to talk about it today.
Can I just ask, are you doing this, making this choice because you think you think nature's built that way?
No, absolutely not.
You think it'll give you more control?
I'm just thinking, really, none of that will matter for what I'm going to tell you about today. The commutation relations don't have to be like this in order for what I'm going to tell you about today to work in a qualitative fashion. I just wanted to tell you what such an algebra might look like. In the last lecture, I put up a much more general class of algebras where these indices I and J ran over all kinds of stuff, and the thing, instead of 1 times delta ij, I had a bunch of operators on the right-hand side, which could have been central charges or non-central charges. This is not, in general, by the way, supposed to be a symmetry algebra. In this particular case, it is. If you insist that it's a symmetry algebra, you run into a famous problem. If you do this with just n equals 1, the representations of this at fixed momentum don't have a graviton in them, the irreducible representation. You have to stick in the graviton helicity as a separate operator. If I want to represent everything in terms of this algebra of operators that I'm putting on null infinity, then I have to have 8 raising operators for the super algebra at fixed momentum. We want to be able to do that, but without having n equals 8 supersymmetry. So what's in general true is that there's an algebra like this in the future and an algebra like this in the past, and those algebras are mapped into each other, okay? But the algebras don't have to be symmetries of amplitudes. Okay? They're just algebras. They are what, in this formalism, you think of as instead of Fock space. We're used to talking about the asymptotic in and out Hilbert spaces in terms of particles. I argued to you, to those of you who were here last time or listened to the recording, that in theories with massless particles, that's not a good basis for the Hilbert space because you have no control over how many very low momentum massless particles have come out in all sorts of directions. And I suggested instead that we should be talking about flows of quantum numbers through the boundary described by algebras like this. And then there's a past algebra and a future algebra, and the S matrix maps them to each other.
So this could be a purely bosonic theory?
Okay. So at this point, all I'll say is I want to have fermions in the theory, and also every example we know, every example that we know that works in string theory has supersymmetry in flat space. So those are reasons to do this. I suspect that there may be some kind of Coleman-Mandula theorem. If you want operators that carry a spin index here, and you've already diagonalized all the momenta, okay? If you want to have an operator algebra with operators that carry a spin index, you're going to end up with too many conservation laws for a Lorentz invariant theory, I believe. But that's not a theorem yet.
So why are you focusing on Lorentz invariance as opposed to a more general rolling scalar background, for example? Because that is generic in string theory and any other theory.
Absolutely. So I'm focusing on Lorentz invariance because a lot of our intuitions about what a good theory of quantum gravity is comes from the Lorentz invariant case. There's also the anti-de Sitter case. I gave an argument last time about why that's a difficult way to look at locality. This will have a much more transparent version of locality in it than the anti-de Sitter case.
So I wasn't thinking of that. I was thinking of the other direction, which is much, much, much more generic. So
I absolutely agree. And our take on all of this, again, following the philosophy of Ted's paper, even if he doesn't exactly buy into it in the words that I say it, is that you have to make a theory space-time by space-time. I'm taking the simplest one in order to illustrate some general principles.
There's some sort of essential tension I've realized I don't understand the resolution of. So you do have something like collections of ingoing and outgoing gravitons in your theory, right? That's
Yeah, I would prefer to call them Sturm-Weinberg jets.
Okay, but there's something like, some version of, gravitational, fields, or gravitons, ingoing and outgoing.
Right.
And you can take a collection of those and build up something like a macroscopic gravitational field. And so that seems a little bit at odds with the statement that you don't have.
No, but there are boundary conditions that we put on to define what we mean by asymptotically flat space. Yeah. You can't put a field that will, in the future, generate a rolling scalar or a cosmology and still say you're dealing with asymptotically flat space. The definition of asymptotically flat space, and what we've always done in string theory, is to assume both the past and future boundary conditions.
Yeah, no, so I'm not talking about the question that was just asked, but, for example, I can send in a collection of gravitons from infinity and build up a strong gravitational field in the middle.
That's true.
But it will die after infinity.
Yeah, so
that's
it's asymptotically
okay.
flat, but it's
okay.
still...
So I know exactly, I think I now know exactly what your question is. Your question is, but the black hole is a different metric than Minkowski space. Okay? And the answer to that, again, goes back to the Bible, to Ted's paper, I think. You have a quantum system which is defined in Minkowski space. It's sometimes got hydrodynamic flows in it, which are described by macroscopic collective variables. And you read Ted's paper, and he tells you that's a distortion of the metric. That's my reading of that particular passage from the Bible. Okay?
Yeah. Well, yeah, it seems like you should be able to take sort of a superposition of these states, like we're familiar with in other field theories and so on and so forth, and really build up a metric.
Steve, the worst you can do is make a black hole. Hawking taught us that's going to decay back into particles. Okay?
Can I help Tom for 1 second on this? Which is just, I think the following comment may be useful. Tom is interested really in finding things that are like scattering experiments from the outside. So he's interested in causality as viewed from its impact on scri plus and scri minus. So if there was a GR solution...
No. I'm going to go inside. I'm going to be local. Absolutely.
Smaller diamonds, right?
Okay.
Yeah, absolutely. Okay, that's the whole point of what we're doing.
But nevertheless, it's only I was going to make the following comment. If there was a GR solution which gave you a time advance in the propagation from scri minus to scri plus, that would be a sharp contradiction with Tom's picture, I think. But those don't exist because they violate the positive energy.
Right.
I wasn't raising that question.
But because they only give delays, there's a lot of room for this kind of picture where, what's the causal? The causal structure is not quite the same causal structure. Or when you try to match up points on the inside, you think you're matching up a small region in Schwarzschild, but really that's an excitation of a large region in Tom's Minkowski space and the causality.
No, I'm just saying it looks to me like there's something that has a lot of the features of a fluctuating metric, but there was the statement there isn't really a fluctuating metric, and that's what I was driving at.
Well, I don't think there's any evidence for...
Degrees of freedom.
Sorry?
Is the statement that there isn't, or that it's equivalent and just captured by some kind of...
Well, in our picture, there is no fluctuating metric. We write down the causal diamonds and their relations as they are in Minkowski space. And we use that in our construction.
Is there effectively
Well, what you'll see is that there is in the scattering theory that we construct the possibility of exciting a long-lived metastable state that will sit someplace for a long time, and if you get anywhere near it, you'll be absorbed into it, and if you wait long enough, it'll start emitting particles with the thermal spectrum.
Sorry, can I just, are the successes of GR coming out in your theory in some way? I mean...
So for example, if someone asked, suppose I have a heavy particle and I want to describe its Schwarzschild field, we actually know how to do that in quantum field theory using perturbative Feynman diagrams. And so our description of that field would be like the perturbative Feynman diagrams. Now, if it's not a heavy particle, but actually I've constructed a black hole, that's inadequate. Our description has a way of describing the black hole. Okay?
Say before you go to the black hole, you can have two energetic particles deflecting each other.
Right.
So that you should be able to
Yes. So what we have succeeded in doing for that case is try to understand the leading iconal scattering, and we've succeeded in the following sense. We get the powers of energy right, and we get the impact parameter dependence correct, but we don't get the Lorentz invariant form, the coefficient for sure not, and we don't get the Lorentz invariant form for the scattering because, as I told you, most of the models I will show you are definitely not Lorentz invariant. We haven't tried to impose that constraint. What's interesting to me about them is despite that, they have all of these other features that we might have expected from the theory of quantum gravity.
So I'm sorry for the distraction. Steve's question got me thinking. I'm wondering now if a finite piece of anti-de Sitter space is a problem in the following sense. In Minkowski space, if you have some observer, like a time like geodesic, and they have, there's some proper time that elapses, then their causal diamond has some finite area.
Right.
If I'm trying to make a theory of or something that could be like anti-de Sitter, maybe because there's a scalar field with a negative value in that region or something, based on this background Minkowski causal structure.
You can. You cannot. You cannot.
Right.
You cannot. Absolutely not.
You agree with that?
I agree with that 100%. It will be a different theory with a different set of Hamiltonians. And this is one of the reasons why, in my opinion, why it's so hard to dig the scattering processes out of a theory of anti-de Sitter space and to talk about what's going on in a local causal diamond, precisely because of this fact that if you wait long enough in anti-de Sitter space, the diamond hits the boundary. You mix your local physics up with an infinite system.
At finite time, my concern was just that for a given proper time interval on this central geodesic, the area of the boundary of the causal diamond is bigger than the Minkowski space. So it sounds like you need more entropy than
Sure. Right.
Which is a short time version of the same problem.
Right. Right.
But then I don't understand. That's anti-de Sitter space. Fine, you can say that's separate. But what if I just want Minkowski space with a scalar field that propagates on it, which
well, some theories are consistent. Some theories are, some classical theories we write down are consistent with quantum gravity. Some are not. I believe that all the ones that are consistent are such that if you throw in anything with asymptotically flat boundary conditions, in the sense that I'm going to say, you come out with something that has the same boundary condition.
That's true. I was talking about making a tiny piece in the center that
then,
looks like anti-de Sitter space.
Right. So I don't know how this is going to exactly work, but the way I believe it will work is that you'll have a system in there which will have hydrodynamic properties that prevent things from traveling freely. So it's like saying that a material changes the index of refraction so that light propagates differently inside the material than it does outside. That happens despite the fact that I'm not changing the metric of Minkowski space.
But somehow in your picture, an observer who has some world line which has 2 seconds elapsed defines what looks like a causal diamond in that effective hydrodynamic flow, which looks like it contains more entropy than the one you would assign in your fundamental structure.
I can't answer a question like that at this stage of where this stuff is. I can only tell you what I know. Okay. So our proposal is to take all of this stuff, and there's some S matrix that maps a past algebra into a future algebra, and how are you going to compute that S matrix? So the traditional way we compute S matrices is by Hamiltonian quantum mechanics, and that starts to introduce lots of problems, because what time are you going to use? And when I want to talk about local propagation, as we were just doing, from whose point of view, which causal diamond am I talking about? And so, as I outlined last time, what we claim is effectively that you have to gauge fix to define time, and you gauge fix in a way that there will be convenient and inconvenient gauge fixings, and the convenient gauge fixings are going to be process dependent. Okay? So the way we think about gauge fixing is we're going to take some time-like trajectory, and we are going to use the time of that time-like trajectory to be the Hamiltonian parameter, the parameter that the Hamiltonian generates evolution in. And we're going to restrict the dynamics in such a way that it makes sense to talk along that time-like trajectory about what in space-time I would call a causal diamond. How do I do that? By taking, first of all, what do I mean by a finite causal diamond period? So our proposal has been these things with this condition can be thought of as spinors that live in the spinor bundle on the sphere at infinity. Okay? The p slash equals 0 condition, p slash q equals 0 condition, tells you that this is a transverse spinor in the light gun frame.
Those are chiral spinors, it looks like.
They are chiral.
So what is that? What's the index structure on that equation?
It's p slash beta dot alpha q
Just
alpha
alpha,
p
yeah,
equals
okay.
0. Slash is with the sigma matrix.
Right.
So that tells you you're talking about spinors on the sphere. And the way we propose to cut this off when we go into a finite area causal diamond is to cut off the Dirac equation on the sphere. That's the same as cutting off the angular momentum on the sphere because of the relationship between the Dirac operator and the angular momentum. The first way of saying it is more general because I now know what to do on any compact Euclidean manifold. And that's part of the story of how you would think about compactification in this, but I don't want to get into that. So what is the cutoff spinor bundle on the two-sphere? It's psi IA, where this is an n by n plus 1 matrix, and that has spins between a half and n minus a half. And this is the chiral, spinors on the two-sphere can be left circularly polarized and right circularly polarized. This is the chiral spinor. It's conjugate, psi dagger, JB, where it's a rectangular matrix flipped on the other side. So dagger means dagger in the Hilbert space, okay? But I'm also transposing the matrix elements and turning it into the opposite thing. And so these are the two chiral and antichiral spinor bundles on the sphere. These are our variables that describe a causal diamond whose area in Planck units is n. Is n squared. And I'm taking the large n limit when I say that. And then this algebra, if I quantize these with the only rotation invariant commutation relations I can write down, I wrote the indices wrong, IA, delta IJ, delta AB. This has a dimension 2 to the n times n plus 1, and so the entropy goes like n squared for large n. And if you want to put the constants in there to fit, what the Planck length is and so on. And by the way, from now on, I'm going to ignore these extra indices. They don't
So these have nothing to do with the new one?
Those have nothing to do with these new indices. Yeah, in the previous talk I did it better. I called these little q and little p. This would have been delta pq over here. Doesn't matter. Okay.
So big N is the dimensionality of small I? Or?
Big N is the dimensionality of small I. Capital A has dimension n plus 1. And there are these very important matrices, Mij, which are psi IA, psi dagger JB. Okay? And those things are things that transform like vectors on the sphere, and then if I take products of them, I get things that transform like the antisymmetric tensor bundle and the scalar bundle. And so among these M's, there are things that transform like two forms that I can integrate over the sphere, and the well-known way of describing such an integral is as a trace of products of these matrices. So the piece of these matrices that can be integrated is the trace of some polynomial in these matrices, and that's going to be the basic building block for the Hamiltonians that I write down.
I'm sorry to slow you down, but I don't actually understand what these psis are and how they relate to spinors.
Okay. So think of this as the angular momentum, the dimension n representation of angular momentum, and this is the dimension n plus 1 representation. And then this thing has in it everything in the tensor product of those two representations, which is spin a half up to n minus a half, and that's just like the cutoff spinor bundle. Okay. by the way, I won't show it to you, but there is a generalization of this construction to any dimension. The dimensions of the cutoff spinor representations work in a rather pretty way in any dimension. And these guys, instead of being matrices themselves, are actually antisymmetric D-2 tensors, out of which you can make matrices in a way that the people who do tensor models have done and we copied. And everything that I say to you today, possibly with the exception of some of the things about scrambling, if I ever get to them, works in any number of dimensions. Okay. Now, when I talked last time about this algebra, I said that in order to define scattering states, I had to restrict the representation of that algebra at infinity. These Q's are measures. Okay, they're actually half measures. They're square roots of nothing. And so to talk about them, I should really integrate them against a function or a spinor bundle element that's measurable. And then what I said was that function has to, at non-zero p, vanish every place except in some small spherical caps. And for 0p, it can be non-vanishing every place except in little annuli around those small spherical caps. And the intuition here was the intuition of Sturman and Weinberg that when I have massless particles in the theory, I have to think about sprays of massless particles with very low momentum coming out. And some of them I can take care of by defining a Sturman-Weinberg jet. Those are the ones that are close to being collinear. And then there are the other ones that go out in any old direction that I want, which I have no control over, and I have to put a cutoff in the Sturman-Weinberg procedure. I have to put a cutoff on the energy and say, I don't know what happens to all of those guys, but what's the right way to say this? The inclusive cross-section where I just sum over everything that happens to those guys is a finite cross-section. That's fine if you don't care too much about unitarity. If you really are worried about the question of is the S matrix for producing and evaporating a black hole unitary, then you have to really know what the whole Hilbert space is and how the S matrix operates in that Hilbert space. And that's why I claim this formulation in terms of currents is better. The p equals 0, one more thing I just want to say, the p equals 0 limit of these things is mixed up with the things that Andy was talking about, the Goldstone modes of the gravitational field at null infinity. Okay? And so I'm including those in what's discussed in the p equals 0 part of Q. Now, there was a question.
Yeah, just why did you, I guess to the extent I understand it, I don't see why you picked n plus 1 instead of, say, n plus 2. Like, what chose the structure of
these are half integral spin things. If I picked n plus 2, I would get only integral spin things. If I picked n plus 3, I would get half integral things, but starting from 3 halves. Okay? So I want to get every spinor spherical harmonic. I'm just taking these guys and I want to approximate them. And so I want to get every spinor spherical harmonic starting from a half up to some cutoff. All right? So I just took the Dirac equation on the sphere and cut off its eigenvalue. Okay? And the eigenvalue cutoff is of order n, but I don't remember the offset. Okay. So that's what the variables are. These are the things I'm going to construct the Hamiltonian from. I'm now telling you about how to make this somewhat loosely defined restriction on states very, very precise. So here I told you, okay, I have these generators, they're measures, I don't yet really understand my Hilbert space, but I want those operators to vanish here and not vanish there and so on and so forth. what does it mean for two functions to vanish in disjoint support? It means that their product is 0. Okay? So when I've gone to this construction, okay, the analog of saying things like this is to say that the matrices M, which represent the functions that can be constructed out of my spinor operators, vanish in certain places. And so what that means is that their products are equal to 0 if they vanish except in disjoint places, and that's the same as saying that they're block diagonal matrices. Okay, if I have a matrix E1, 0, 0, 0, and a matrix 0, E2, 0, the product of those two things vanishes. Okay? So the precise analog of this picture is that I'm going to take some causal diamond with a very, very large value of n. Okay? Let's take it halfway to our current cosmological horizon, where I can neglect the fact that I'm in de Sitter space for a while. And it's huge, but finite. This restriction on states is the restriction that, as operators, the matrices M take on this block diagonal form, with the blocks EI being such that the sum of EI is much less than n. Okay? And this block down here, which has a size which is not much less than n, because it's n minus the sum of the EI, that's what I'm going to identify with all of this zero momentum junk out here. Okay? So this very explicit constraint on my incoming states in the matrix variables is the translation of this rather loosely defined picture, which I based on thinking about that algebra in Sturman-Weinberg jazz.
So when you say it's a constraint on the incoming
States. It means these things vanish as operators when applied to the incoming states. Now, not every incoming state will have the same constraint.
Right.
So how do we define scattering states? We say where the jets are, where they're coming in from, and that's it. So this is a definition of the constraint on the states, state by state. So any state that has the following properties, that the M's have this block diagonal form, okay, with the sum of the EI's much less than n, I will consider a legitimate incoming state into the causal diamond at radius n.
But I'm confused. As you say, the constraint is different state by state.
Right.
And this constraint doesn't satisfy linearity. If I propose two states that satisfy the constraint separately with different block diagonal decompositions, surely this position doesn't satisfy.
Why not? It's an operator equation on the states.
It's an operator. How is it an operator equation on the state?
Oh no! I'm sorry. You're absolutely right. Yeah. No, I'm talking. Right. We're not talking about superposing states with 4 pions coming in from the north, south, east, and west, with a state with 16 pions coming in from a bunch of other directions.
But you're saying if we try to make this position, it's not an allowed physical state we can discuss, or just that it's not something we want to call a scattering state?
No, the Hilbert space will be built out of, this operator algebra defines a Hilbert space.
Right.
Okay? There are subspaces of that Hilbert space which satisfy these constraints. And now if you want to superpose things that involve different subspaces, then those, of course, won't satisfy these constraints. Okay? But since the subspaces give me a basis for all the allowed states, I can use that basis and talk about
so these are the easy states to discuss.
These are the easy states
The
to
more general
discuss.
states are allowed. You're not ruling them out. It's just
Absolutely. But the point is, if I tell you the S matrix element between any two states satisfying these constraints, then I've got everything.
Yeah.
bilinear.
Fine.
So you say that these states are not very special. In a sense.
They're very special.
They
do not form a
complete
complete set in this Hilbert space.
But
The entropy deficit, very
yeah,
interesting
because
question.
they look
The
like
entropy
being
deficit
low
of
entropy.
states of this form is of order the sum of EI times n. It's actually somewhat bigger than that, but when n is much larger than the sum of EI, this is the entropy deficit. That's an incredibly important relation. It tells you the way you should think about energy is you have a Hilbert space in a fixed causal diamond, most of whose states don't carry what we will call energy asymptotically. The energy is a constraint on the entropy. It's an entropy deficit. That's what defines what the energy is. And the thermal behavior of everything will follow from that principle. Okay? Because it says, suppose I had a random state in this Hilbert space, which I can if the causal diamond is small enough. If I had a random state, the probability of picking out a state that I would say had some number of particles with energies EI would be exponential in the sum of the EI times n. And that's the right scaling for the Hawking temperature, the de Sitter temperature, etc. And by the way, this formulation of what energy is follows from the black hole formula in de Sitter space. If you look into de Sitter space at the entropy of a black hole of mass much less than the de Sitter radius, I mean its Schwarzschild radius is much less than the de Sitter radius, then the black hole entropy formula tells you that the energy of that state is the same as the entropy deficit, and that's a derivation, if you will, of the Gibbons-Hawking relation. Okay.
Or you could just say it's an ultimate factor in the general Fermat sum.
Absolutely, but this explains how I can have a system which is effectively at infinite temperature, okay? Look in the set of all the states and still find this particular quantum number energy distributed according to a Boltzmann factor with a temperature that depends on the horizon size. So this is crucial to everything that we do, and I'm very glad you caught that at this point. Okay. So now what I call this stuff energy, I want to argue to you that for an appropriate choice of the way these Hamiltonians behave, this thing I call energy is actually conserved. Okay? So now I want to tell you what the Hamiltonian looks like, okay, in this sector of the theory, okay, with a fixed number of jets. So what it is that H is equal to the sum of P naughts of I, I'll call it, over the I small blocks. I'm using I for too many things. P naughts of super B over the B small blocks, plus 1 over n squared times the trace of P of M. Now, this is the Hamiltonian operator, not for all times. The Hamiltonian operator, as I argued last time, in a setup like ours, that if you want to impose the idea of locality, the Hamiltonian operator along some proper time, some trajectory, has to have the property that if I go from here to here and then look at going from here to here, if I want this operator algebra to commute with everything in this larger diamond that I consider space-like to it, okay, then it had better be that the Hamiltonian that describes evolution from here to here only acts on the variables that live in that smaller diamond. And the definition of live in that smaller diamond I'm now about to give you, I'm talking about evolution along some time like geodesic in Minkowski space. For that geodesic, I'm going to take a central time. I want things to be time symmetric around some arbitrarily chosen central time. And I'm going to look at propagation in bigger and bigger diamonds by unpeeling them, okay? If I propagate, I have a Hamiltonian that propagates from here to here, okay? And I'm going to call that Hn of t, where t is the size of this causal diamond in the sense that capital N was the size of the biggest causal diamond. And then that'll be the same as, so let's call this minus little t. This is Hn of plus little t. And that will only operate on the Hilbert space in this diamond that has of order t squared fermions associated with it. How do I choose those t squared? Well, I choose the t squared by saying this is a particular time-like geodesic. There is an SU2 rotation symmetry around that time-like geodesic. I'm going to organize things so that from the point of view of this trajectory, as I add space to my causal diamond, I add angular momentum modes. In that way, I can keep SU2 invariants at every stage of the game. Okay? So that's how I'm going to add things in. Now, one thing you have to understand, if I look at a huge causal diamond, these commutation relations are invariant under un cross un plus 1. There are many, many, many different copies of SU2 inside of that group. Okay? This group effectively is not SU2 on the two-sphere, but it's the group of all area-preserving mappings on the two-sphere. That's another result from fuzzy geometry that you may or may not know, but it's a correct result that the unitary group on square matrices, and this is the generalization to the action on spinor bundles, it's the group of area-preserving diffeomorphisms in the limit that you add all the angular momenta back in. And there are famous results in topology and so on that there are lots of SU2s in there, and you can make lots of different spheres if all you care about is area. I'm going to talk about a particular SU2 from the point of view of a particular observer. Okay, that is not the SU2 of some other observer. Of course not. In general, if they're geodesic observers, so that they have an SU2, those will be related by some kind of Poincare transformation, the different SU2s. But that's only in the limit. For finite causal diamonds, they're not. Okay. So now, how do I construct this Hamiltonian? Well, what I want is I want to put a coefficient 1 over n squared in front of this polynomial here. Okay. So that everything in here, I'm not telling you that there isn't, sorry, this is, now let me be more careful about what I write. This is the Hn of little t, and then this is 1 over t squared, where I haven't told you anything about how these coefficients depend on t yet, except that for large t, they all scale like 1 over t squared. Okay? Why 1 over t squared? Well, it taught us that if I put 1 over t here, that would be an operator of order 1. Its operator norm would be of order 1. If I put 1 over t squared here, this operator is going to 0 at infinity. All of the interactions in this theory are going to come via this operator. Okay? How are they going to come? Well, what's going to happen is I'm going to throw in a state that looks like this, that has block diagonal matrices. in very large causal diamonds, this P will have terms that involve fermion creation operators for all of the different matrix elements of the matrix. And so it will turn on and off zeros. It'll turn off guys here, it'll turn on guys over here, okay? And that will, as I'm going to argue now, that will preserve the sum of the total energies, but the form of the constraint is going to change. Okay, so let me try.
Just a very naive question. Trace PM is not a unitary operator, right?
That's right.
So it's not bounded in any, I mean, inside.
We're in a finite dimensional Hilbert space, I guess.
Yes, but you eventually, you put a cutoff, so you would like not to depend on the cutoff. Or you don't care that you depend.
That's what it taught us. It taught us that if I take T.
So is there an order of limit involved here?
But shouldn't the power of T depend on the degree of the polynomial?
No.
Well, if you have
all single trace operators have the same scale.
I thought you have to divide, the corresponding coupling has to be, take Young-Mills. The cubic has G, the quartic has G squared. One goes like 1 over square root of n, the other goes 1 over n. Shouldn't there be an extra T dependence inside the
I think you're right. I think you're right. Excuse me. We've always neglected.
If you have a multi-m vertex,
Okay.
it will produce more powers of n.
Right. But then there was already normalizable. I mean, here.
Yeah?
What? There's no constraint on renormalizability.
No,
because
it's
these are
fine.
finite
It's
operators.
so finite.
Yes.
I mean, if you think in terms of n or t.
Okay, so please excuse me. What I really meant is there's this 1 over t squared scaling where that's 1 power bigger than the usual Latouf scaling.
Yeah.
That's what I really meant. Yeah. Yeah, you're right. Okay. So, Jesus. Let me argue to you that as a consequence of this form of things, the thing that I called E, the sum of the EI, is conserved. Okay? Why will that be true? So if I think about starting from some large causal diamond and coming in, I have of order sum of EI times n constraints, and then there's plus some finite number of constraints, some number f. Okay? Now, act with this Hamiltonian. At very large n, okay, this Hamiltonian doesn't do anything. It acts, but its action is bounded. So it can't change the state by very much. This polynomial, by the way, has a finite order. I know it has to be bigger than 7, but it has a finite order that will be hopefully fixed by Lorentz invariants. I don't know what it is aside from the fact that it's finite and n-independent. So now what happens is when I propagate further in, the h-in part of the Hamiltonian, which is the only part that I'm talking about right now, I'll tell you about what happens to the rest in a minute. The h-in part of the Hamiltonian, as I propagate in, acts on many fewer degrees of freedom. So even if I get down to small t's, where the action of the Hamiltonian is dramatic, okay, then the Hamiltonian can't change of order n constraints. It's changing, in the places where it's big, it's changing only a small number of degrees of freedom. And so it can't affect most of them, modulo what's going to happen with the rest of the Hamiltonian that I haven't told you about yet.
So what's the meaning of T? Is this a coupling or
T is time.
Time. T is time.
T is time. So this is, I'm using large n scaling, but n is being swapped with time in this story, and it's related to time by the entropy formula,
When you
basically.
say acts Do you mean as the generator of time translation?
Yes.
So you're continuously shrinking your diamond in a time step.
These are
dt.
discrete. These are discrete time steps. I'm shrinking the diamond discretely by adding one angular momentum
But then
mode.
how does h act?
Or subtracting one. Sorry.
How does h act?
By e to the iht, e to the minus iht. So this is the Hamiltonian in the sense of the time-ordered product formula. Okay. And by the way, if you shrink by one angular momentum mode, each step, that's a Planck step in time by the entropy formula. Okay. So it's discrete time evolution. I don't think of that as crucial. You could interpolate between that in any continuous way you wanted, such that in these discrete time intervals you've got the same thing. It wouldn't change a single thing I'm saying.
Also, I'm kind of confused that so H involves the matrix M. M is built out of psi, which has a particular n associated with it. So I can imagine.
No. So what I told you is the way I'm going to restrict it as I go to smaller causal diamonds is I'm going to lower the indices on n according to the rule given by some particular SU2 subgroup of the group of area-preserving diffeomorphisms, or this unitary group. So I pick some SU2, I say, according to that SU2, these things come in angular momentum multiplets. Every time I'm going to a smaller causal diamond, the variables are labeled by fewer indices. You have every right to ask me what happens to all the other variables. And I'm going to tell you that in good time, except I don't know, Steve, what do we do about it? The other lecture starts now.
Well, the next talk is at 12:30.
It's 11 o'clock.
There's a condensed matter.
Oh, in
Yeah.
Oh, it's in here?
No.
Oh, no. Oh, well, I guess it's up to people,
Okay.
if they want
Sorry.
to go to the other talk. If enough people want to go, maybe we should stop, but, well, it's up to the audience.
We report you to stop.
I don't know, is it a review talk? The title is interesting, but is it a review or a professional?
I don't
You
know
don't-
the
you don't-
details.
What is the talk?
Disentangling tensor networks or something of that kind.
So, I think it's up to the collective here. I'm
I
not going to
was
make the
hoping to
decision.
go and at least check out the other talk.
We'd then have to continue another time, probably not next week, since next week is pretty full. So that's the, well, or
Although there's lots
tomorrow,
of-
well, no, okay. Actually,
No, I can't. I have to leave. I'm going to.
that's right.
I'm going to
Yeah.
home this.
So it'd be, yeah.
How much did you get through what you had planned for today?
Half.
We interrupted a lot.
Yeah, of course.
Okay, if you want to quit, let me just tell you what we claim to have proven about these models. Okay, so what we claim to have proven about these models is the following. If I look at what's going on as I've described it to you, you can see that the interactions are concentrated in small causal diamonds. And the scales are given by the Planck length and so on. So the interactions are local. If I take a causal diamond of some small size, think about all of the E's that came in from the big causal diamond. Well, some of those I've just thrown away. They're not included in the Hilbert space of this causal diamond. That corresponds to things that are somewhere else in space and that I can't see over this short period of time. So if the E that comes into my causal diamond still satisfies this inequality, then what you can argue is that what will happen is you'll still get a state that satisfies a constraint, because if the sum of the EIs is much less than n, okay, that means that you have of order, much less than t, okay? That means you have of order t matrix elements you have to turn on and off. It's not easy to do that in just one Planck time. So you will generally get another state that satisfies a constraint, and you'll get a picture that looks like this, where some number of particles come in and some number of particles come out. Then you can ask, well, what about the other things that weren't in this causal diamond? Let me take a trajectory, and this is defined really relationally to the incoming state, which captures, let's say, all of the rest of those particles. Suppose there were just two clusters that scattered. There will be, and again, assume the ones coming into this set of diamonds satisfy that inequality. There will be a particle scattering like vertex. And it could be, if this one was in the past of that one, that one of the particles from here is really the particle that comes into there. Okay? So the constraint on the Hamiltonian, the out Hamiltonian of this guy, in a bigger causal diamond, which includes this process, is that the out part of the Hamiltonian of this guy, which I haven't talked about so far, has to have in it a copy of what went on over here in the in Hamiltonian of this guy over here. And that says that they have the same physics in that overlapping tensor factor of their Hilbert space. So imposing that set of constraints for all possible trajectories, you can sort of see things that start to look like time-ordered Feynman diagrams. Some number of particles coming into a little local vertex, some number of particles going out, possibility of particles propagating between two local vertices before they go out to infinity. So this has Feynman diagram-like descriptions of scattering. But if I don't satisfy this inequality in some causal diamond of size t, then it no longer makes sense to say that the system is not disrupted by this incoming state. This constraint is very, very special. It's constraining almost all the degrees of freedom. It will no longer be satisfied. And if this Hamiltonian over here is a fast scrambler, then in a time of order t log t, it will equilibrate the whole system. So now at that point, I don't have any particles coming out. I have this lump of stuff that's in equilibrium. Okay, and the picture of that is viewed from far away is that I have this time-like trajectory along which a lump of stuff at equilibrium propagates. Okay? And that lump of stuff will randomly, every once in a while, with probability e to the minus epsilon times its size, get back into a constrained state, which can then be propagated away from it as a particle. So the claim is that the model has in it kind of crude versions of what we'd like, both for particle physics and black hole formation and evaporation, with the right scaling of all the temperatures. And the final thing I'll just tell you, I mentioned this before, is that you can also consider just the large impact parameter scattering of two massless particles. And if the polynomial has order 7 or greater, the 7 or greater comes from the fact that you have to have enough terms in the polynomial to turn on and off all of these guys. In order to get that thing to scale correctly, you have to involve this. And the only way you can involve this is by turning on all of these guys here. And if you do the counting, you're doing kind of Brillouin-Wigner perturbation theory, and you need an order 7 polynomial to have an action that turns these guys on and then turns them back off again so that you can come back to a state described just by these two blocks. And two things I want to emphasize about that. A, you get the right scaling for Newton's law, basically, but from these trace formulas, okay? But number two, you only get it by virtue of having this huge set of degrees of freedom that don't show themselves as particles. Now in field theory, if I work in a physical gauge, I get it by solving the constraint equations. That's where Newton's law comes from. Here, it's coming from, if you will, integrating out the very low momentum stuff. Okay, so
Did you say what is B0B?
No, I didn't. I'm sorry.
Okay.
I didn't have a chance to do that.
Because
Basically, it's 1. It's the unit matrix in that block.
Okay.
Plus something of order 1 over the block size squared times the same polynomial. Okay? And
it looked to me that this operator preserves the rank of a matrix. You wanted to reduce T by 1 unit? I'm a little bit confused.
I reduce
Since
T
you
by
take the
1.
full trace, this
That's
operator...
in this operator, I'm taking the full trace. Here, I'm taking the trace just over the block diagonal part. So there's, as always in scattering theory, there's a contribution from the scattering states, from the incoming energy of the scattering.
But this Hamiltonian was supposed to change T by T plus delta, no? Or T plus...
Right. But it doesn't change the size of the blocks.
It doesn't change.
It doesn't change the size of the small blocks unless they're completely outside of the smaller diamond.
Okay.
So thinking about the blocks as particles, then you can sort of see how it works. The blocks are all coming in from infinity. If I go to a small diamond around me, some of those blocks are going to miss that diamond completely.
That's it. Okay.
And so those are not included, and the ones that are included as constraints on my variables, those are the ones I can see in the scattering integers problem.